Guys, let's take a few minutes and look at the confidence intervals multiple choice practice solutions. So 87% got the first question correct. So this is just interpreting a confidence interval. We're 95% confident that the mean time for response is between 2.8 and 12.3. This was the most commonly chosen wrong answer. People said we're 95% confident that a randomly selected time. Remember, a confidence interval is not about capturing anything except the true population parameter. So that's the goal. The goal is not to capture a sample value. The goal is not to capture a randomly selected value. The goal is to try to capture the true population parameter, not a randomly selected one. So 83% got the second question correct here. So it's a sample size of 25. That sample size will produce more variability than an estimate or a sample size of 50. So why is that? That's because when you build the standard error, the standard deviation is going to be in the numerator. Then the denominator is the square root of the sample size. That formula is on your formula sheet. So if you want more variability, you need a smaller denominator. If you want this expression, this fraction, to be bigger, that would be more variability. You need a smaller denominator, so you're dividing by a smaller denominator. If you want less variability, then you need a denominator that's bigger, and that will make the fraction smaller. So 82% got number 3 correct. So the correct answer here is that n is 100 and a p-value close to 0.5. That will give you the greatest standard deviation for the sampling distribution. So remember, the formula for the sampling distribution standard deviation is on the formula sheet. It's p times 1 minus p all divided by n. So if you want a greater standard deviation, what you want to be using then is a smaller denominator. So you want to use one of the answers with a denominator of 100. And a greater standard deviation also means you need a numerator that's large. So the largest possible numerator comes from using 0.5 for p. So here, working on the sample size needed to obtain the margin of error. So the first thing that I did was, I'm going to show you the work here first. So we want a margin of error of no more than $5. So when we do this for means, though, we have to assume that we know what the standard deviation of the population is, because the truth is, to get a t-score, well, a t-score is used only when we already know the sample size, so we can calculate the degrees of freedom. If we don't know the sample size, well, then we can't calculate a t-score. So you really should use z-scores when you're trying to estimate the sample size you need for a margin of error for a mean. So there is that standard deviation for the population of 35. We want 90% confidence, so 1.64, 1.645 is a good z-score to use for that, and I'm just going to do the work to solve it. So I'm going to multiply both sides by the square root of n, and then we're going to divide both sides by the 5 to get the radical by itself, and then we can square both sides in order to get rid of the radical, and that gives us 132. So the truth is, of the answers over here, the closest one by far is the 133. That's the correct answer for number 4. So 88% got number 5 correct here. So the correct answer is down here at the bottom. The sample proportion minus the margin of error is greater than 0.5, which provides evidence that more than half of all likely voters plan to vote for Taylor. So here, this is about using the confidence interval in order to make a conclusion. So we have a point estimate of 0.55, and if you add or subtract 0.03 to that, you get a confidence interval from 0.52 to 0.58. So that's what they're trying to describe here. The lower boundary, the sample proportion minus the margin of error is still greater than 50%. So we have evidence that more than half of voters intend to vote for Taylor. These were the two most commonly selected wrong answers. So it's not possible to draw a conclusion. Well, yeah, we can draw a conclusion here because what we want to do is actually build the confidence interval from the values in the statement above, and then we can make our comparison. So the other thing that people said was, here, just a second, the Taylor must have the same proportion of voters. The proportion of all likely voters who plan to vote for the candidate Taylor has to be the same as those the proportion of all likely voters who plan to vote for Taylor must be the same as the proportion of voters in the sample who plan to vote for the candidate Taylor, because the data were collected from a random sample, but that's not true. The sample statistic can very much vary from the actual population parameter. That's the whole point of having a margin of error. So here, number 6, 89% got this correct, and I was thrilled with that. So of these simulated sampling distributions, which is the best estimate of the parameter? So this is the one that's the best estimate of the parameter. We are told in the statement of the problem that the true value is at 0, so this one is centered around 0. That would mean that it is unbiased, and then we want as little variability as possible around that 0, so I want the least amount of variability that I can. So this one is unbiased, and it has the smallest amount of variability. Those three are biased because 0 is not at the center of the simulated distribution. And here, this one has more variability. 0 is at the center of the distribution, but it has a much larger spread than this one. So that's why that's the one that's the best estimator of the parameter. So here, 82% got question number 7 correct. So you're told that this 95% confidence interval for the proportion of residents that favor offering incentives was calculated to be, so here's the point estimate plus or minus the margin of error. So really what this says, 0.54 minus 0.05, that's 0.49. And 0.54 plus 0.05, that's 0.59. So the confidence interval goes from 0.49 to 0.59. So now our job is to figure out which of these statements is correct, and it's this one. So at the 95% confidence level, the estimate of 0.54 is within 0.05 of the true proportion of all county residents in favor of offering incentives to high-tech industries to build plants in the county. So there you go. So the wrong answers, or the most commonly selected wrong answers, are here. In repeated sampling, 95% of sample proportions will fall within this interval. That's not true, so you have no idea where your sample proportions will fall. In repeated sampling, 95% of all the intervals that you could build in repeated sampling using the same population and the same sample size and the same method, 95% of the intervals will capture the truth. But sample proportions don't have to fall within this one particular interval. So this answer is also wrong. In repeated sampling, the true proportion of all county residents in favor of offering incentives to high-tech industries to build plants in the county will fall within this interval. Well, there's nothing sacred about this particular interval. In repeated sampling, the true proportion of residents, blah, 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 that true proportion of residents will be captured in about 95% of the intervals that we could build within repeated sampling. But these two answers are wrong because these two answers at some level are obsessed with this one particular confidence interval that we simply built up here in the stem of the question from one particular sample. But every sample could yield a slightly different interval. So those are the problem. It's just about, those statements are just about this one particular interval, and the truth is that one particular interval just isn't that sacred. So question number 8, 71% got this one correct. So here's the correct answer. The width of the new interval would be about 1/2 of the width of the original interval. So the most commonly chosen wrong answers were, well, most of them. There was a variety of people that chose a number of different answers. So people said the width of the new interval is about 1/4 of the width of the original. They said it could be about the same as the original, is about 4 times the width of the original. So maybe it would help to actually look at the answer here and the structure of the standard deviation. That's the formula that I put here that you can get off of the formula sheet. So understand, here is the sample size of 200. So I don't know P and I don't know 1 minus P, and it doesn't matter because look, 200, if you break it down, if you factor it, It's 4 times 50. Okay, so take a look at what that is then. Dividing by 4 is the same as multiplying by a fourth, and if you take the square root of a fourth, you get 1/2. So bottom line, it's not going to be the same width. You change the sample size, you are definitely going to change the standard deviation. And look, you have a larger sample, so the bottom answer here doesn't make sense either. You're not going to be 4 times as wide. A larger sample of 200 compared to 50, it's going to make the interval narrower because you're taking the standard deviation down. So look, if you chose the 1/4, you were almost there, but the 1/4 is under the square root. You need to take the square root of that. That's why the 1/4 is the wrong, and the correct answer is the 1/2. So here, 82% got this question correct. So which of the following statements has to be true about the sample sizes? So you have distribution 1 and distribution 2. So the sample size of 1 has to be greater than the sample size of 2. So notice distribution 1 has a much smaller spread. Well, that comes from using a larger sample size. Distribution 2 has a bigger spread, so that would come from using a smaller sample size. So the wrong answers that people selected, people said the sample size of 1 should be equal to the sample size of 2, but it's not about being equal because I can see these two distributions have different spreads, and the sample size is what controls the spread. So it's not going to be equal. Same thing here, the sample sizes can't be compared based on the graphs. Now you can definitely compare them. Because you know that the sample size is what has the effect on the standard deviation. So remember, there it is, the formula for the population standard deviation, and we knew, it said in the question that this was about a sample mean. So this is straight off of the formula sheet. It is the standard deviation of the population divided by the square root of n. The square root of n is in the denominator. That means that n, the sample size, is going to affect the spread of the distributions. So absolutely we can compare them, and they can't be equal. As n changes, that denominator is going to change, and that means you're going to get a difference in variability. So the last question. So this is a confidence interval. We've seen this a number of times. There's our point estimate. There's our critical value, and here is the standard error of the statistic because I have substituted in the p-hat and the 1 minus p-hat. So a city's interested in building a waste management facility. 100 randomly selected residents from this area were asked, do you support the city's decision to build a waste management facility? Of the 100 residents, 54 said no, 4 said yes, and 42 had no opinion. So we're building a confidence interval using this structure that's advertised here. So which of the following statements has to be correct for this confidence interval? So this is the correct answer. This confidence interval is not valid because the count of successes is too small. So we need to go through and check our conditions. The other commonly chosen wrong answers, people said this confidence interval is valid because a sample size of more than 30 was used. Well, guys, that's the central limit theorem. That involves means, not proportions. The other answer that I saw that was incorrect, this confidence interval is not valid because no opinion was included as a response category for the question. Well, understand, there are still, though, only 2 options because you're trying to build a confidence interval. So look, you can say people said yes, or people didn't say yes. You can combine the no's and the no opinions into one group. So you can still establish this as 2 groups, success and failure. So here, take a look. Doesn't matter, there are still only 2 outcomes. I suppose this was a better way to say it. You could say yes, or you could not say yes. No or no opinion can be lumped together. So in terms of the conditions, then look, randomness is met, no problem. So independence is met because we're considering this to be a city. So if this is actually a city, 10 times 100 would be 1,000. That would be less than or equal to the population of the city. So the problem here involves the success and failure counts. Normality is not met because the number of successes is only 4. 4 people said yes, that's less than 10. The number of failures, so the people that are not saying yes in total, that's 96. That's greater than or equal to 10. So that's why the confidence interval up there is not valid, because the number of successes, the success count, is too small in order to use this method that we've been studying. So, and don't forget here, I mentioned this earlier, but obviously I put this on the PowerPoint. I forgot that I stuck this here. So look, the confidence interval is valid because a sample size of more than 30 is used. This is important. Remember, more than 30, n is greater than or equal to 30. That's the normality condition for means based on the central limit theorem. And this question is not about means. This question is about proportions, but it's good to review it because this unit test will cover confidence intervals for proportions and it covers confidence intervals for means.